Okay, so for the second part, I will try to run a bit faster because of the time. The second part is how to use the map to do navigation. Okay, to do autonomous navigation. Autonomous navigation means the robot is going to decide how to move from point A to point B. Okay, you only tell the robot where to go and where is the starting point, and the rest is done by the robot. And this is autonomous navigation. Okay, so but before we can talk about autonomous navigation, we need to understand a few concepts. Okay, I try to make it short, but this concept I think is very important. So I will tell you what are those concepts, and I hope you can read more by yourself. Okay, so the important concept over here is what we call the robot motion planning. Okay, so robot motion planning. So as you know, the objective of the autonomous navigation is you tell the robot the starting position and you tell the robot the goal position, and you give the robot a map, and the robot's supposed to do the rest by themselves. Okay, by itself. So how the robot want to move from point A to point B with a given map, it needs to do the motion planning. Okay, for the motion planning, it involves, for example, the path planning, which means you need to create a path. And then after you have created the path, you need to control the robot with the localization in each point to move the robot from point A to point A1, A2, A3 until it reach point B. Okay, so one example that I can explain over here is we use the A-star algorithm. So A-star algorithm is a very, I think it's a very popular path planning algorithm that make the robot move from point A to point B by planning the path. Okay, and the concept of A-star is like this. Okay, so you try to imagine, like, okay, if you look at the image on the right hand side, sorry, yes, right hand side, the blue color is the wall in between, and then the starting point is green, and then the end point is red. So the robot's supposed to move from the green point, move to the red point, but how to determine the path and how to move, that is what we call the robot motion planning. And in order to do this, in the A-star algorithm, we need to, do the planning with certain policy. For example, like the policy here is path with shortest cost. Okay, I'm not putting shortest distance, but cost is because like the shortest or the smallest cost sometimes might not be the distance. For example, if you take the train, you want to move from station A to station B, for example, and then in order to move from station A to station B, you might have several routes. For example, like road path number 1, path number 2, path number 3. And path number 1 maybe is the shortest, but it takes longer time because the more difficult, for example, like the road is not so smooth and it's more difficult. So it may not be the shortest route, but it is actually the fastest way. Okay, possible. Or another thing is maybe you want to find the road that give you the cheapest train fare, for example. So it depends on what policy you put in. What is the policy that you want to set, like which one? Okay, so for example, over here, we want a very simple policy, which is the shortest path, which means like the travel distance is the shortest. Okay, so for A-star algorithm, moving from the green point to the red point, first, we try to discretize the whole field into several small steps, into small steps. So you can see the box is actually to discretize the steps. So every time when the robot moves from one box to another box, it is considered one step. Okay, so it depends on how small you can discretize. If you can discretize until very, very small, then yeah, it becomes very accurate. Okay, right. So it depends on how small, but the concept is you discretize into several steps. So the next thing is you want to find the step from the blue box to the red box. So how to find this? So you try to imagine when the robot starting from the green box, then you can see surrounding it actually have nine boxes surround the green box. So these 9 boxes is the possible second step, right? And then when you move to the either one of the next the nine box, you will have additional next third step and so on. So this is very similar like chess. You move this and then from here, from this state, you move another one and so on. So it's a step, first step, second step, and third step. Okay, so in order to visualize this step, I would like to show you what we call the Tower of Hanoi or Hanoi Tower. Okay, so this is a very famous mathematical algorithm example that to explain about state space and search problem. So state space and search problem is like in every step, it is considered one state. One state is the record of the whole thing when the robot moves one step. Okay, so you can see from state number 1 to state number 2, you got 9 possible options, right? From the green, and then you want to go to the next one, you got 2, 4, 6, 8. Sorry, 8, 8 possible, right? So plus the middle one is 9. So the green color, and then you got 8 possible next step. So if you put into this Tower of Hanoi, it is very similar. Like from the top part, you got this is one state, and then this one state you got 2 possible next step, and from this state you got another 2 possible next step, and so on. So this is a search space and state space and search problem. Okay, in order to visualize this, let me show you a very simple demo of Tower Hanoi in order for you to understand. So let me search Tower Hanoi Tower, for example. Okay, so so it is something like a game. I think when you look at it, you understand this. Okay, so the idea is we have like this. So this is considered one state. So the idea is how many move I need to take in order to move this 3 circle to this side. And every step that you move, for example, I move like this. This is one move. So consider from state number 1 to state number 2. Right. Then I move this thing to, oops, sorry, this one, this is state number 2. Right. Okay, if I restart this, from here, I actually have 2 options. So that's why from state number 1 to state number 2, I have 2 options. So if you come back here, from state number 1, I have 2 options. Then if you proceed to this step, then you have another 2 options and so on. So if you can consider this as this, so for example, the first one, I have so many options here, then I move here. Then from here, I got this several option, then I move here and so on. So it is moving like this. Okay, it is moving downwards like this. Yeah, like this. Okay, right. So you understand this concept. Then every time when you want to go to the next step, what is the policy you choose? It depends on the policy that just now I said. For example, like I got these 8 boxes. Apparently, like these boxes is the closest to this. So that's why I choose this. Then from this few option, this is the closest to this. So that's why I choose this, and so on, and it continue until I reach this. Okay, so this is the concept of motion blending and this search space and state space and search problem. Okay, I'm explaining this in a very brief way, but if you want to know more, please read more by yourself. And I think this is a very classical topic in computer science in terms of searching problem. Okay. Okay, right. So I'm not going to explain more on this. You can read by yourself. So now I'm going to show you how we do things in ROS. Okay. So so just now we got the map. Okay, so the next step is we want to use the map. So we have the map. We want to use the map to move or to make the robot move from point A to point B. Okay, so I also explained like for this to work, the robot need to able to do localization. And in order to do localization, we are using this AMCL. Okay, the AMCL software in order to do this. So this AMCL, the adaptive multi-color localization, you can read more from Google, from Wikipedia to understand the concept. You can even read the mathematical explanation on this. You can find a lot of resources online, multi-color localization a lot. And you can go to the ROS wiki to understand how it is implemented in ROS, right? But if you want to skip all this thing, okay, let's go to how we run this, okay? So in order to run this, you can refer to the Turtlebot Autonomous Navigation using a known map. Known map means the map that you already built, right? You can go to that link, but I'm going to show you the demo of this. Okay, so now let's proceed with the demo. Okay, so in order to proceed with the demo, I need to again bring up this thing. Okay, so now let's assume I have already done this. Okay, I already have the map, right? So now let me do the cleanup. Let me clear all this thing. Okay. Okay, so I clean up the whole thing. You close all this thing. Okay, so the same thing, the first step is to create the gazebo model, which is the virtual model. Okay, so I will create the virtual model again one more time. So I'll come back to this, the turtle board example. Okay, I want this thing to be smaller. Close this thing here. Okay, so I zoom it in. Okay, so I have the model here, which is good. Tilt a bit so that you can see clearly. Okay. Bigger. Okay, right. So I have the model the same. So the second step is I need to run the AMCL, right? So AMCL, and you can see when I run the AMCL, I need to specify where is the map file. So you need to give the AMCL the map that you have created, okay? But ROS Launch, board, gazebo, AMCL demo, right? Right, okay. So you need to do the map file something, okay? But I'm going to use the default one because like the map that I created is not nice. So I'm going to use the default one, which is the complete one, right? So I didn't type anything here. I will get the default one. But if you change the model, you create a new file, you need to put in your map file over here, okay? Right. So this one just a demo, I just use the default map, which is the map of this. Okay, Autumn they receive mean it received the Autumn from the virtual robot. Okay, then I run the RVs in order to see the visualization of my sensor. So it's the same thing. ROS Launch, Turtle Board, RVs, Launcher View on Navigation, Launch. Okay. Okay, so yes, so I can do the navigation. Yeah, so wait for my RVs to come up. Okay, right. So you can see now the RVs look a bit different. Let me make it smaller so that you can see clearly. Smaller. Still very big. Okay, so I have fields smaller, please. Okay, I have like this. Maybe this one can be bigger. Okay, so I zoom out, and then I need to rotate in such a way that you can understand. Okay, now it makes sense, right? You can see the left and right So the right-hand side is the map of the left-hand side. Can you see? And then also you can see the initial gas. You can see a lot of small this arrow. So this one I explained just now is the particle that when the robot receives the initial sensor data, it try to say like if the robot stand on one of this, it give the same. I mean like it give the matching sensor reading. Okay, so this is the particle filter, the arrow, and as the robot moving, you can see this arrow actually converge and become less and less. Okay, but anyway, so over here, so okay, so now I already have this. So now I already can do the navigation. So there's two ways to do the navigation. Okay, so let me show you the simple one first. The first way is we can show you the concept by using the GUI. Okay, so now this is the starting position. For example, I tell 2D pose estimation means I give the starting position. But because the starting position is the same, so it doesn't matter. So I just say I start from here, and then it looks, the starting orientation is this. Okay. Unless this is very wrong, then yeah, you might redo this. But okay, so because the simulation is correct. But in real world, the robot might not always stand on the starting point. So you need to use this 2D pose estimation to tell AMCL where is the starting point, where is the actual location of the robot with respect to the map. Okay, so you need to tell. But because it's simulation, you always start at the correct same point. Okay, so it doesn't matter. Right. So now I want to ask the robot to move. So I need to give a goal, which is the point B. So to give a goal, I use this 2D navigation goal. Okay, I press this. Then, for example, I want the robot to come here. So I press here, and then I drag to the front to show the final orientation where the robot's supposed to start. Okay, so I release. Then you can see the robot start to have all the grid, and then it start to have this line. So this line is the path planning. Then every time it moves one grid, it will do the localization, and it will scan to see everything is okay until it reach the goal position. So yeah, so this ROS navigation package already help you to do the autonomous navigation. Everything is done without you actually knowing what is actually happening down there. Okay, but this is that. And then you can see like this, the color, this one is the potential field. Is the sensor that to give you to give the robot some idea like how much space it has in order to move around. Okay, so just to illustrate, can the robot do path planning that go through, for example, like go through this narrow passage? Okay, so let me put a point here, for example, and then I want the robot to see front. Okay, for example, see here. Okay. And let's see. Then you can see the robot won't cross like this because it will do the path planning and it go to the shortest distance. So it will follow this, come to this point. Can you see? Yeah. So and sometimes because of the space is too wide, so it don't have much reference. So sometimes it might need to scan a few times in order to pass the narrow passage. Okay, so this if you want to improve this, you need to tune the parameter. Okay, but anyway, you can see like the line is here, so it's correct. It's just that the sensor might be not so accurate for it to do the localization. So when this thing happens, means the localization is not really good. I mean, it has some confused state where it not so sure if the correct correct location, the location is the correct one. So that's why it will turn a few more round to get more sensor data in order to confirm the localization is correct. But anyway, it actually reached the goal point. Okay, so the next thing that I want to show you is not only the obstacle in the map, it can actually use it for path planning, but if you have suddenly add a new, for example, I add one new obstacle here. For example, I put somewhere here. Okay. So this obstacle is how to say, is in the middle of this. Where, okay, maybe this one is a bit, okay, maybe I need to put it a bit because it's too tight. Maybe later it can't actually move out. So let me pull it out a bit. Okay. Hopefully it's okay. Okay, right. So now I add one more obstacle which is not appear in the map. So let's see if the robot will actually crash on the new new obstacle because it is not in the map. Okay, so I ask the robot to come back here and let's see what happened. So the obstacle is somewhere here, but you can see when the robot reach here, it will realize that it got a new obstacle here. Then it tried to avoid. You can see it tried to avoid. See, it tried to avoid. Try to move this. So which means the algorithm include dynamic update. So for example, like if you have someone actually walk past the path planning of the robot, then the robot will actually change the path or try to update the path so that it will avoid the newly detect obstacle. So you can see, although this part is not in the map before this, but it update in AMCL. Okay, so this is what we call the dynamic obstacle avoidance and so on. And yeah, even the AMCL actually take care of this as well, right? So yeah, this part is I think it's a very intelligent for autonomous navigation and so on. Okay, so I already like demonstrate this thing nicely. I'm not sure if you have any question you want to ask, but because of the time constraint, next I want to explain if you want to do this using source code. Okay, so just now I'm using this 2D navigation Go, right? So if you want to do this, you want to write this as a program. So how you want to do? Basically, in order to write this as a program, we already have one example in RoboCup at Home Education source code, the open source repository that give you the idea, the example to pass or to determine or to give the instruction for the robot to do the navigation. Okay, using code. So over here, please, you can open up this. Sorry, yeah, this location. Yeah, this file, location A over here, right? So it's under. So let me show you where is the file. Okay, before this, where's my? Okay, this one. Okay, so let me show you where is the location of that. So first is like you ROS CD. You go to your this one, and then navigation. Okay, so inside this package you have what we call the script, right? So I show you inside here I have one script which is the navigation.py. So I nano show you this. Sorry. .py. Use navigation, not navigation 2. Okay, navigation 2 is for other demo. Right. So for this one, so this is the node for you to send the command of the navigation point, the goal point. Instead of pressing on the RVs, you can use this. You run this node, it will tell the system to move to that point. Okay, so over here, what you need to do is you just need to update this X and Y value and theta if you know the orientation. So this, you update this in coordinate, the XY coordinate. So you can specify the goal point by using the XY value here, writing in this code, and you can run this example like this, which means you run everything the same like just now. Then up to you have everything already ready, and the which means is just now when I stop at before I press the 2D navigation goal. Okay, during that state, If you run this node, then the robot will receive the goal point and move to the goal point. Okay, yeah, it's like this. So all you need to do is by the end you just launch this navigation.launch. Then you set the initial point, then the robot will move. Okay, so this is how you do for that. But you might want to ask me the question. So how to get the XY value, right? Okay, so let me show you how to get the XY value. So the XY value, you can get it from here. Okay, you can get it from here. So how to get the XY value is you press this publish point. Press this. Once you press this, oh, sorry, I think I close. Okay, yeah. So once you activate this publish point, when you move within your map, can you see like there's 3 value down there over here, right? Over here, there's a 3 value. So this value is X, Y, and Z. But Z, because it's 2D, so Z is almost close to 0, so it doesn't matter. So important thing is the first 2 points. The starting point, somewhere is here, right? So if you go down, you will get positive value. So 0.9 for X, 0.97 for X, 0.2 for Y. And if you go somewhere up here, because the starting point is somewhere here, right? So if you go up, then you get -2 and then positive. If you go this side, then you get both negative. So this is the XY value using the map coordinate system. So you need to tell, because when you supply the map to AMCL, it will follow the map coordinate system, and you specify your goal location, which is what we call the waypoint, using this value. Okay, so in actual practice, you might want to define, like, for example, this is the toilet, for example. Okay, so the toilet, I'll choose 1 point and I will record this X and Y value. For example, this is kitchen, then I will take this value and I will write this thing into my source code so that I can tell the robot where to go by telling the goal point. So this is how we do the navigation. Okay, right. Due to time constraint, I will straight away get Jupyter Robot to do the demonstration. Is that okay? Then Jupyter Robot, please show the demo for the real robot.
Okay.
Okay. Yeah, please take over the display.
Yeah.
Right. So everyone see like what I've done. Jupyter Robot will show using the real robot.
Since we already set up the maps here, so
okay.
Okay.
Yeah, so the first thing is to load the map that we already built, okay, in the AMCL.
对 After bring up our robot.
Okay, so first bring up the robot.
Then
so this is the AMCL demo.
Yes. And
okay, then you need to specify the map file. Okay, so Jupyter Robot have to specify the map file of for the office. So it need to write the map file and then the value of the map file, the path to the map file. Okay, and you specify the AMCL file, not the PGM. Okay, you specify the AMCL file, the YAML file, sorry, YAML file. Right. So after you run the AMCL, then you run the RVs. So it's the same as the simulation for a real robot. So now we have the map file, the RVs loaded with the map that we created. So we try to put the map the same orientation as the real world. Then now we can give the 2D navigation goal, and the robot will start to move to that point.
Yeah.
Yep.
Like here.
Okay. You just now you do a 2D post estimation is the starting point, right?
Okay. Yeah.
Okay, so you can see like one path appear. So it's very similar like the simulation. Then the robot start to move. So the whole effect is the same as you just saw in the simulation, right? So Jupyter robot have moved from the starting position to the end position. Oops, how come it fly there?
Because I click this.
Okay, right. So you can always use the 2D post estimation to put back the robot to the current position. Can you try one more point? Yeah. Okay, so now the robot start to move to the goal point. It's a bit tight. Yes. Although it's quite tight, but yeah, it still reached the goal point.
Yeah. And 沙发前面挡一下。
So you want to try the obstacle, okay?
Yeah.
So now we try to add one obstacle which is not appear in the map and see how the robot behaves.
And we can use this RQT tools to adjust the parameter.
Yeah. So just now I said like when the localization is not very smooth, we can actually tune some of these AMCL parameters.
Yeah.
But you can see like there are many parameters for this DWA, right? Yeah, the path planner. So usually what parameter you adjust?
Maybe there's
Max
velocity of yeah.
Oh, the velocity of the theta, which is the velocity of the turning. So sometimes if you see the robot keep on spinning, which means maybe the spinning velocity is too fast, so it always overturn. So that's why I keep on spinning.
And maybe this inflation layer.
Oh, okay.
Yes.
So this is the safety region. So it tells the robot how big the space for the robot to, how to say, consider if it can pass by a narrow passage. Because if you have, for example, like you try to imagine the robot is wearing a safety, safety balloon, for example, okay, safety that thing. So if this is too big, then the robot might not able to cross a very narrow door. So you might want to adjust this, but you cannot adjust too small because then the robot might collide to some very narrow passage. So you need to adjust this accordingly. Yeah, but anyway, just to give you idea that there are actually many parameters that we can tune in order to improve the path planning and also the navigation. That's why it's very important for you to understand the robot model and also the navigation algorithm and so the navigation tools and what kind of parameters you can tune. Okay, right.
Okay.
Okay, so thanks, Jupyter Robot. very smooth demonstration, and I think everyone already like see. Even just now when we have an obstacle, a dynamic obstacle, so the robot actually choose another path to go to the top. So it can actually consider the path planning. I would say like it's a very intelligent. So it really consider the map. It gives the shortest path, and also it will accommodate, or it will adapt to new dynamics obstacles. Right, so with that, we have show you everything for today. Right, so thanks Jupyter Robot. So let me show you the last slide. Okay. Okay, so you can try out using the coding one to see if you can make it work, but it should work the same as the GUI. So I want to skip. In fact, I want to show you this video, but I think I will skip it due to the time. So this video is actually, this is the former Google car team manager, that it show how the progress or the development in Google car or Google autonomous self-driving car project. And you can see inside there a lot of algorithm, a lot of tools they use are very similar to what we are doing in mobile robots, because like it actually come from the same root. So eventually, whatever that you learn here, you can actually expand. And yeah, if for those who are interested in autonomous driving and so on, I think this mobile robots, this navigation thing is the basic that you have to learn. Okay, but yeah, you can learn with everything with simulation to get the basic. Then eventually you will, you can proceed and learn about autonomous vehicle. Okay, so for the last assignment for today is I will encourage you to attempt this exercise. So you try to combine the speech interaction with the robot navigation. So for example, just now I show you how to to record several waypoint from the map. So you got, for example, like point A is go to the kitchen, point B is go to the living room, point C is go to the bathroom, point D is go to somewhere, the main door, and so on. Then you can create a robot that you tell the robot go to kitchen, go to living room, go to whatever. Then the robot, when it receives this, it will convert the living room to the waypoint XY and give it to the location A. That's just how I show you. So how to do it? I think by now, if you have done the exercise for the previous one, I think you know how to connect this together. Okay, so you connect the speech interaction result. For example, with from the Google speech, you get the result. Then you channel the result to the navigation.py, that node. Okay, so you probably subscribe it. Then from there, you say like, if you heard, for example, kitchen, then kitchen represent location A, for example. Then location A, X is something, Y is something, then you put the value, you give it to the navigation.py and run it, and then the robot will move from the current position to location A. That is how we do it, right? And you try to do this with like at least 3 waypoints, and you can do everything with just your gazebo simulator. So even without any robot, you can still do this whole development. Okay, so with that, I would like to close the session today, because we are 10 minutes over the ending time. But I would like to open for question and answer as well. So I would like to invite once again our LOC to briefly summarize what I've just said, and also to open the Q&A to our Thai community as well.
โอเคครับทุกคนก็วันนี้ก็จบกับเซสชันนี้ไปแล้วนะครับก็มี assignment ทั้ง2เซสชันเนาะโดยในส่วนของเซสชันแรกที่เป็น Slam Map Building เนี่ยก็คือเขาให้เราไปทำการสร้างแบบที่เป็น environment ใน Gazebo เนาะแล้วก็ทดลองทำ post process แบบที่เขาบอกก็คือลองใช้ตัว Grim หรือว่าใช้ Photoshop เนี่ยในการลองถมบางจุดที่บางครั้งเป็นโต๊ะแต่ว่ามันเห็นแค่ขาโต๊ะอะไรประมาณนี้นะครับแล้วก็ ทดลองที่ใส่เป็น several key location เนาะก็คืออาจจะเซตห้องไว้ประมาณ 2-3 ห้องหรือว่าเป็นจุด waypoint ประมาณ 2-3 จุดประมาณนี้นะครับส่วนในส่วนอีก assignment เนี่ยก็คือ assignment ของอันนี้เนาะก็คือเป็นอันที่ในเขาพยายามจะให้เราเนี่ยรวมกับสิ่งที่เราเรียนมาก่อนหน้าเนาะก็คือในส่วนของที่เป็นspeed interaction กับตัว robot navigation นะครับก็ให้ทดลองดีไซน์แล้วก็สร้างตัว navigation เนี่ยบนROS ที่เป็นGazebo Simulator เนาะโดยที่เรารวมกับในส่วนของ Speed Interface เช่นอาจจะเป็นการสั่งให้หุ่นยนต์เดินไปทางนี้เดินไปตรงนี้หรือว่าช่วยหยิบของไปตรงนี้ให้หน่อยอะไรประมาณนี้นะครับก็เขาก็ขอเป็น at least 3 waypoint เนาะก็คือลองสร้างสัก3จุดเนาะเช่นมีห้องครัวห้องนั่งเล่นแล้วก็มีนอกบ้านอะไรเงี้ยครับก็ลองดูนะครับแล้วก็เหมือนเดิมครับอัปโหลดขึ้น GitHub ได้นะครับแล้วก็ตอนนี้เปิดในส่วนของ Q&A session นะครับสามารถที่จะยกมือถามนะครับสามารถถามได้เป็นทั้งภาษาไทยและภาษาอังกฤษนะครับโอเค Jeffrey.
All right, so you have any question? Or else I have to close the session because we already like over the time. You have anything you want to ask? Any question from the audience? Anything for today? The content for today. I know it's a bit rushed today, but we have a lot of things to show you. So I hope you can review by yourself. Yes. Turn on your mic.
Yep. The question from the last lesson, we used the USB camera.
Yes.
I cannot run your example code. Can I share the screen? Or maybe you close the section, the classroom.
Okay. All right. Okay, so we can do this after I close the session. No problem. Right. Okay. Yeah. So is there any question regarding today's class for the navigation? Is there any question you want to ask regarding today's class?
ขอถามเป็นภาษาไทยนะครับว่าเมื่อกี้นะครับที่บอกว่าเรากำหนดพารามิเตอร์ที่ว่าจะให้แบบโรบอทผ่านทางแคบได้มันคือตัวไหนกันแน่นะครับเมื่อกี้มันมีอยู่2ตัวผมเห็น
he asks for the parameter to adjust for the robot can move around the narrow area.
So just now I mentioned we mentioned two. One is you can control the correction speed. Okay, because just now we realized that when the robot turn, it always overturn. I mean, like it overshoot. So we try to slow down the maximum theta velocity. Theta velocity means the turning velocity. So that is what we adjust. Another parameters that we adjust is the inflation size. So inflation size is what is the size that we want to set so that we tell the robot this size is the safe space. So for example, your robot is like, for example, 1 meter in diameter. You might want to save the safety for like 1.5, for example. But sometimes if you save too big, you cannot pass very narrow door. So you might want to adjust this inflation size according to your robot model. Of course, you can adjust to very tight, but when you adjust to very tight, then a slight, how to say, error or how to say overshoot, it might affect or the robot might crash to something. So how much safety you want to give is depends on how much you can fit in. Of course, if you make the robot move faster, then you need to make the safety size bigger. But if you make the robot move slower, then maybe the size can be as close as the body. But this one, it very depends on the practical. When you run the robot, you see how much tolerance or how accurate your robot, because it also depends on how accurate your moving your mobile base as well. So if your mobile base is very accurate, then you can give very tight tolerance. But if not very accurate, then maybe you want to give a bigger one. So there's no definite finite what is the best value. There's no best value, but you need to adjust according to your development and also your environment. Okay, so but just now we adjust these two value, the speed, the robot speed, and also the size. Okay.
ขออนุญาตนะครับคือว่า inflation size มันขึ้นอยู่กับว่าเซนเซอร์ของเราจะจับระยะได้ใกล้สุดเท่าไหร่ด้วยไหมครับ
He has about the inflation size is up to the sensor spec as wait a minute.
Sorry, can you repeat again? I don't really get your question.
Okay. He want to know about the inflation layer parameter is depends on the sensor spec that the sensor has resolution of sensor. Yes, it depends on resolution of sensor.
Okay, so the inflation size basically to tell the system how big is the body of the robot, for example. Okay, but sometimes we set this value a bit bigger than the actual value because we want to have some factor of safety. Okay, because for example, you set like your diameter is 1 meter, but sometimes when you move too fast or your base or your sensor is not very accurate, it might be like move a bit to the left or to the right. Then if let's say you have very narrow this factor of safety, the tendency for it to how to say to touches or clash into something is very high. So of course it depends on the operating condition as well. For example, like your flooring, is it very slippery or it's very hard to move, and also your accuracy of your motors, for example, your wheelbase, and also of course your sensor, because your sensor, if let's say the tolerance, how to say, you use the unit like resolution, yes, is how accurate is your sensor will also give will also need to be taken into consideration when you want to set the factor of safety, is because, for example, your sensor have the accuracy of, for example, like 0.5 meters, for example. Then you set your factor of safety is bigger than 0.5, then it is very risky. Your factor of safety have to, I mean, like the size have to be much bigger than 0.5 so that you won't, although you have maximum error, you still won't like clash to the boundary or clash. So it depends. Yeah, but yes, you're correct. The sensor accuracy is part of the consideration factor as well.
โทษนะครับคือว่าสมมติว่าเหมือนกล้องแอตตาเราสมมติว่าจับระยะทางได้ใกล้ที่สุดที่ 0.4 เมตรดังนั้น inflation size เราก็ได้ไม่น้อยกว่า 0.4 เมตรใช่ไหมครับต้องมากกว่านั้นอะไรแบบนั้นไหมครับ
He asked for the if he used the Asta camera, the spec is the nearest data that it can receive is 4 meters, and he asked that for the inflation layer is be more than 4 meters.
I think the inflation is actually smaller than that, if I'm not mistaken.
0.4 meter.
Yeah.
Oh, okay, 0.4 meter. Sorry.
Yeah, I think it's less than that.
ครับก็น่าจะต้องเล็กกว่านะครับ
Which means if you look at the inflation size, I think it's much bigger than the robot itself actually. But how small can you reduce? That is depends on how accurate is the sensor and how fast you move the robot. So if you can move the robot very slow, then your robot is safer.
Thank you.
Yeah, but one way to find out is try, do experiment, test, and you will know how it moves, because there are actually a lot more parameters for you to tune. So yeah, I can't have the best solution for you because a lot of this parameter is for you to tune based on your operating and also your environment condition. So that's why you have the GUI, the parameter for you to do the adjustment, is because it really depends on how you design your robot. Okay, is there any more question about this navigation? Right, if no more, then I would like to close this session. Thanks a lot for you attending this session. It's very nice. And I hope you enjoy the content and also you learn something from this. And I really wish you good luck for your development. And I hope you can share your development with us. For example, like you have a custom made robot and you can make it navigate, or you have like some formula to adjust the parameter or so on. Feel free to share with us this information. Okay, so thanks a lot for coming, and I really hope to see you next week. And also not forgetting Jupyter Robot, thank you for the support and also for the demonstration, and also my Thai LOC for your language support. Right, so I will close this session, and if you have anything you want to ask after the session, yes, I'm still here. Then for the rest of you, I wish you good night, and I will see you next week. Bye-bye.